Let's do another example, and this is about the survey of 1,230 households across the US, with 37 of the households that had more than one smart TV. The objective is to compute a 99% level of confidence, find E, the margin of error, for the proportion of households with smart TVs. So let's compute the necessary factors here. First of all, E equals Z sub alpha divided by 2 times the square root of P hat times Q hat divided by N, the sample size. So remember, P hat was 37 divided by 1,230, which is 0.0301. And Q hat is 1 minus P hat, and that is 0.9699. For the 99% confidence level, Z sub alpha divided by 2 is 2.576, as we saw in the previous table of values that we made up. So therefore, E is equal to the margin of error is 2.576 times the square root of 0.0301 times 0.9699 divided by 1,230, and this is equal to 0.125. So this is our margin of error. So the confidence interval, the 99% confidence interval, 99% confidence interval is equal to the point estimate, P hat, plus or minus the margin of error. In other words, that's equal to 0.0301 plus or minus 0.0125. Was 0.0125. Okay. So this means that our confidence interval is between 0.0176 less than P less than 0.0426. So that is our confidence interval, where P, of course, is the population proportion. So in a sentence, if we use percentages, we can say that the true population proportion is between 1.8% and 4.3%. So in a sentence, we can say with 99% confidence, one can predict that the true population proportion of US households with more than one smart TV is between 1.8% and 4.3%. And you always want to state the conclusion in form of a sentence. Writing it this way is okay, but it's not really a complete answer. You need to explain what this really stands for. Let's look at this when we use technology. And in this case, it's Nspire, which is similar to the TI-84. So we go to statistics, and we go to confidence intervals, and we go to 1 proportion Z interval. So now we input our data for successes. There were 37 households that had more than one smart TV, and the total number of households were 1,230. and we wanted a 0.99 confidence level. So now hit OK, do enter. So here are the numbers, and you can see that the lower confidence level is 0.017, the upper confidence level is 0.042627, etc. Here's our p-hat that we had computed previously. Here's our margin of error, and of course n is equal to 1230. So that's just a quick example how we can use technology. TI-84, Inspire, probably TI-83 is about the same. So the sample proportion is p-hat, and our confidence interval is p-hat minus the margin of error, and then p-hat plus the margin of error. And so this would be the lower limit, and this is the upper limit. This means that if we know the upper and lower limits, we can compute the margin of error because it's half the width of the interval interval. So we can say that the margin of error is the upper limit minus the lower limit, all divided by 2. That would be the margin of error. So that is half the distance of the interval. So from the previous results, what that means, the lower limit was 0.0175 and 0.0426. So then the margin of error would be 0.0426 plus 0.0175 divided by 2, and there would be, of course, our margin of error, E equals 0.0125. Next, we're going to talk about the requirement checks to compute confidence intervals for proportions. First of all, the sample is a simple random sample. And we discussed that in chapter 1 and 2. Simple random sample. The second requirement is that the conditions for the binomial distributions are satisfied. We are counting a characteristic that does or does not occur from a fixed number n of independent trials. So the check would be that n is less than or equal to 5% of the population size. Now, if the sample size n is large enough for the sampling distribution to be normal, that's called the normal approximation to the binomial. There are at least 5 successes and 5 failures. So what that means is that there are at least 5 successes and 5 failures. So x would be the number of successes. They must be greater than or equal to 1. And then n minus x, the number of failures, would have to be greater than or equal to 5 also. there's something else. When X is not given in the problem, here's how we determine successes and failures. So here's what we do when X is not given explicitly in the problem statement. We determine the number of successes by multiplying n times p hat and check that n times p hat is greater than or equal to 5. And failures would be equal to n times q hat, and then check that n times q hat is greater than or equal to 5. Let's look at an example on the death penalty. A Quinnipiac University poll asked 1,780 U.S. adults nationwide whether they favored or opposed the death penalty. 63.2% of those surveyed were in favor. So we are supposed to check the requirement and then compute the 90% confidence interval for the true proportion of the population who favor the death penalty. So let's look at the three requirements. Number one, is that a random sample? Random sample. And that is, the answer here is yes. That's what good polls do. Number two, is n less than 5% of the US population? So that each person can be treated as an independent binomial trial. And so 1,780 is certainly less than the US population, so that's a yes. Now, the third requirement was about the number of successes being greater than 5. And let's look at that. So x would be equal to n times p hat. And remember, what is p hat? P hat is 63.2%. So p hat is equal to 63.2%, or 0.632. So then x equals n 1,780 times 0.632, and that's equal to 1,125 people. So they're the ones in favor. And that number is certainly greater than or equal to 5. So that's a yes also. And now for the number of failures, would be n minus x. The number of failures would be 1,780 minus 1,125. So that's equal to 655. 655 people who oppose. People oppose. And that number is certainly greater than 5, 655, so that is a yes also. So all the requirements have been satisfied. I input the data for x as 1,125. Oops. As so in this case, it's not from StatCrunch, it is from NSpire or TI-84, basically the same thing. So our confidence interval would go from 0.6132 less than p less than 0.6508. So that's our confidence interval using technology. Okay. And so in a sentence, we can say with 90% confidence, one can predict that the true population proportion of US adults who favor the death penalty is between 61.3%, and 65.1%. So you always want to conclude your results in form of a sentence. Again, with 90% confidence, one can predict that the true population proportion of US adults who favor the death penalty is between 61.3% and 65.1%. To compute this manually, we find E, and again, E is equal to Z sub alpha divided by 2 times the square root of P hat times Q hat divided by N. And now for the 90% confidence level, we know that Z sub alpha divided by 2 is equal to 1.645. Again, you can consult the table we made earlier, or you can look it up. So it'd be 1.645 times the square root of, so P hat was 0.632 and Q hat is 0.368 divided by 1,780. So that means our margin of error is equal to 0.0188. So then the confidence interval is then 0.6320 plus or minus 0.0188, or if we do it graphically, then it looks like this. Here's 0.6320, and here would be 0.6132, and here would be 0.6508, and so this is 0.6320 minus 0.0188, this point here, and this point would be 0.6320 plus 0.0188. So here's the upper limit, and here's the lower limit. So that's how you can do it if you do it manually. Let's look at another example here, and that is about the alcohol-related death. In 2010, the National Highway Safety and Traffic Administration reports that 3,434 randomly selected fatal traffic accidents in California, or of those, 1,198 were alcohol-related. So let's check the requirements. 1, 2, and 3. Again, 1 is pretty easy. It's a random sample. Random sample, yes. Yes. And N is less than 5% of the population in California. population. And then number 3, x, the number of successes, would be equal to 1,198. 1,198 alcohol-related accidents. And that's certainly greater than or equal to 5. And then the number of failures, n minus x, let me squeeze that in here, n minus x would be then 3,434 minus 1,198, or 2,236 non-alcohol related accidents. And that's certainly greater than 5 also. So in other words, we satisfy the requirement that the sampling distribution is approximately normal. Using technology, I input all the numbers here for x and n and the confidence level. And here are our lower and upper limits of the confidence interval. You can see that right here is the lower limit, and here's the upper limit. Here's our p hat, and here's our margin of error, and here, of course, is n. So in other words, our confidence interval states that p is between 0.3279 and 0.3698, or the true population proportion of the accidents is between 32.8% and 37.0%. That's our confidence interval. And now we're going to write the result in form of a sentence. So in form of a sentence, we can say with 99% confidence, we can predict that the true population proportion of California's fatal car accidents that are alcohol-related is between 32.8% and 37%. Let's look at the relationship between confidence level, sample size, and margin of error. So first of all, what effect does increasing the level of confidence have on the margin of error? Well, let's take a look at it. For a 90% confidence level, we have our z sub alpha as minus 1.645 and positive 1.645. So in other words, this area here is 0.90. For the 95% confidence level interval, this is minus 1.96 and plus 1.96. So that means here now the area is equal to 0.95. And for the 99% confidence interval, we have 2.576 on the minus side, minus 2.576 and 2.576, because we want 99% in the middle. So in other words, setting higher confidence level causes wider E. E gets bigger. Let's look at the effect that increasing sample size has. So if we compute a 99% confidence interval with n equals 100, then it's about 22.3% here, 35% in the middle, and it is 47.3% on the upper limit. And if we go to n equals 500, then the lower limit would be 29.5%, and then 35% in the middle, and then we have 40.5%. And then when we go to the n equals 3000, then we get 32.8%. And the lower limit, 35% in the middle. And then for the upper limit, we have 37.2%. And that makes sense. Remember that the margin of error is z sub alpha divided by 2 times the square root of p hat q hat times q hat divided by n. So as n gets larger, the ratio gets smaller. So in other words, the margin of error shrinks as n increases. You can just think about that. If n is equal to 100, that is a certain number. But if n is equal to 500, then the ratio will certainly be smaller, and so the margin of error will be smaller. So the overall goal is precise prediction. Precise prediction. We want to narrow E with high confidence. High confidence. Then we need to take larger samples. Take larger samples. Or take a larger sample. Oops, I'm sorry. So the overall goal is to have a precise prediction with a narrow margin of error, and that means, and with high confidence, that means we need to take a larger sample. So you saw it here how this works. If we just change the sample size, and here's the mathematical explanation. As the denominator gets greater, gets larger, the fraction gets smaller. So how do we find the correct sample size? Suppose we want to collect sample data in order to estimate some population proportion with the desired accuracy. The question is, how many sample items must be obtained? Can we choose a really small margin of error and then find the sample size needed to get that accurate in prediction? Well, let's look at the formula again. E equals z sub alpha divided by 2 times the square root of p hat q hat divided by n. And so now we solve for n. Solve for n. And there are many different approaches you can use. And I'm going to leave it as an exercise for you to do that. One way to do it is to square both sides and then solve it for n. And again, there are different approaches. But no matter what approach you're going to use, the sample size n is equal to z sub alpha divided by 2 to the second power times p hat times q hat, all divided by e squared, by the margin of error squared, divided by e squared. So this is the correct expression for n, sample size, given that you want a certain margin of error. So the sample size needed to reduce E, the margin of error. To find the minimum sample size needed to create a confidence interval for the population proportion P with specific error of estimate E, use one of the following. If you have a preliminary estimate for P hat, the sample proportion, then N is equal to this expression that we just wrote down here. N is equal to z sub alpha divided by 2 squared, z sub alpha divided by 2 squared, times p hat times q hat divided by e squared, the margin of error squared. And then note that n is always rounded up. always rounded up to the next integer. Okay. And here a preliminary estimate for p hat means we've already done at least a small sample or with a previous sample in order to have an initial p to start from. And if we don't have a preliminary estimate for p hat, then we use a different approach. It's quite similar actually. It's z sub alpha divided by 2 squared times 0.25 divided by e squared. Let's look at an example. You wish to estimate the proportion of fatal accidents that are alcohol-related at a 99% level of confidence. Find the minimum sample size needed to be accurate to within 2% of the population proportion. Okay, so here's the information we have. We know for a 99% level of confidence, z sub alpha divided by 2 is equal to 2.576. Okay, we need that from this formula here. And since we don't have a preliminary estimate, we use this formula here for n. So z sub alpha divided by 2 squared times 0.25. Now, the other thing is within 2% of the population proportion. So that means that we want a margin of error. We want e to be 0.02. Okay, so e squared. So then with the numbers, z sub alpha divided by 2 squared would be 2.576 squared times 0.25. Again, that's from the formula here. And then we have 0.02 squared. And that, if we increase it to next, okay, that turns out to be 4,147.4. So we round it up to 4,148 accident reports are needed. Reports are needed to have a 99% level of confidence. Now let's say if a preliminary study of 140 fatal accidents found 49 that were alcohol related, now we can compute our preliminary p hat. So p hat would be equal to 49 divided by 140, and that's equal to 0.35. So that means q hat is equal to 0.65. So z sub alpha divided by 2 times p hat times q hat divided by e squared. So we have, again, 2.576 z sub alpha divided by 2 is equal to 2.576 squared, and now we have 0.35 times 0.65 divided by the same margin of error squared, 0.02 squared, and that now is equal to 3,774.09. So that says, so that means that with the preliminary study, you can reduce your needed sample size to 3,775 accident reports. So that's about 373 fewer accident reports. So in other words, it reduces the amount of work you have to do. So this goes to 3,775, since we round up to the next integer. Since we already have an estimate for p hat, we use the formula for n as z sub alpha divided by 2 squared times p hat times q hat divided by e squared. So now let's do the numbers. For a 90% confidence level, z sub alpha divided by 2 is 1.645. So we need to square that. So p hat is 0.824 times q hat, and then there would be 1 minus 0.824, that's 1.176, divided by, since we want to be within 3 percentage points, so e squared would be 0.03 squared. And this number is 436.04. So we round it up to 437 because we round up to the nearest integer. So in summary, we can say that with the preliminary study, she would need to sample 437 people to make her estimate with a 3% margin of error at 90% confidence. The next part assumes that she does not use any prior estimates. So then we use a formula for n as z sub alpha divided by 2 squared times 0.25 divided by e squared. So that's equal to 1.645 squared times 0.25 divided by 0.03. So a little heads up here that, like within 3 percentage points, you want to always convert that into decimal notation like we did in the previous example. Okay, so that turns out to be, so that is equal to 751.67. So in other words, she would need 752 samples if there's no preliminary study to make an estimate with a 3% margin of error at 90% confidence. So you can see that even with a preliminary study, the number of samples goes down dramatically, from 752 to 437. That's a huge decrease. So let's go over a quick notation summary. So P would be the population proportion. So to make sense of what we're talking about here, it's really important to know the notation. Again, P is the population proportion. P hat is the sample proportion, or x divided by n. And x is the number in the sample with a counted characteristic. N is the number of sample values. E is the margin of error. Alpha is the complement of the confidence level. So if the confidence level is 90%, then alpha would be 10%. Alpha divided by 2 is the area in each tail outside the central area, and the central area is determined by the confidence level. And then z sub alpha divided by 2 is a critical value, the z-score separating the central area equal to the confidence level from the area in the right tail. Let's close the section by analyzing polls. So when analyzing the results from polls, consider this. The sample should be a simple random sample. So the sample should be a simple random sample, of course, and the confidence level should be provided. It is often 95%, but in the media it's usually not, or it's often not reported. And then the sample size should be provided also. And then, of course, the sampling method itself is important as well. But what is not so critical is the size of the population. That is usually not a factor. In the previous example or problem, we noted that a Pew Research Center poll randomly selected 1,007 adults and asked if each person knew what Twitter is. The sample results are that N was 1,007 and P had 0.70. Check the requirements, then find the 95% confidence interval estimate of the population proportion P. So let's look at it real quick here. Is it a random sample? Yes, it says here randomly selected. And P, or rather N of 1,007 is certainly less than 5% of the US population. And the number of successes, N times P, 1,007 times 0.7, that would be equal to 705, and that's certainly more than, it's greater than 5, so N times P is equal to 1,007 times 0.70, so that's equal to 705, and 705 is certainly greater than or equal to 5. And then Q would be, or N minus, or the failures would be, 1,007, 1,000, excuse me, N, so the failures would be N minus X, pardon me. N minus X would be 1,007 minus 705, and that's equal to 302. We don't know Twitter, and that's certainly greater than 5 also. So the requirements are met to assume that this is randomly distributed. And now to find the margin of errors and the confidence interval. So when we use technology, we find that the margin of error is equal to 0.0283, so about 2.8%. So our confidence interval would be 0.70 plus or minus 0.0283, or 0.6718 less than P, less than 0.728. Here I wrote for you the formula in case we don't use technology. We do it manually. Z sub alpha divided by 2 times the square root of P hat Q hat divided by N. And again, we get the same answer. To summarize this in a sentence, we can say with 95% confidence, the data from the Pew Research Center would predict that the true population proportion of US adults who know Twitter is between 67.2% and 72.8% if you write it as percentages. And so based on the results, it can be safely concluded that 75% or more of adults know what Twitter is. So here's a great observation. Since 75% is not in the confidence interval, it would not be reasonable to conclude that 75% or more of adults know Twitter. So then in summary, we can say since 75% is not in the confidence interval, it would not be reasonable to conclude that 75% or more of US adults know Twitter.